Good morning, YouTube. Today I want to talk about how does paper chromatography work. So recently we did a chromatography lab, and now some of you are probably wondering, how does this work? Why does chromatography do what it does? Great, that's a great question to ask. Let's answer that question. And the first thing that we need to understand, we need to talk today just for a moment about water itself. Water, H2O. Here's the structural formula for water. Water looks something like this. It's two hydrogens combined with an oxygen. Now, this bond here, the oxygen-hydrogen bond. So let's talk about the electronegativities. The electronegativity of hydrogen is 2.1, and the electronegativity of oxygen is 3.5. And the difference here, 2.1, is 1.4. And that means that this bond between the hydrogens and the oxygens is very polar. So these shared electrons here are being pulled toward the oxygen so that the oxygen is going to get a partial negative charge. And these hydrogens are going to get partial positive charges because they have the electrons being pulled away from them. So can you see that one side of the molecule over here has a positive charge and the other side of the molecule has a negative charge because of these two polar bonds? So I like to represent water as something like a triangle. Think of water something like this. And in fact, for a lot of my explanations, we will use just a symbolic triangle for water. And up in this is the oxygen here, and then these are the hydrogens. So I want you to imagine this side of the triangle being positively charged, the base, and the tip of the triangle over here being negatively charged. So we have opposite charges here. That's important to remember about water because water is going to behave in particular ways because of this difference in charge, this dipole that water has because of the polar bonds. And I don't know if you can see this, but I've got a lot of little triangles down here that we're going to use in our explanations. And each little triangle, I want you to think of the tip of it having a negative charge and the base of it having a positive charge. Okay. Now let's talk about paper. Paper is made of cellulose made of starches, and glucose being the monomer that makes up paper. And I want you to imagine that this is a sheet of paper here. Glucose, the glucose molecule has on it negative spots of negative charge and positive charge. That there are polar bonds within a glucose molecule. And those polar bonds give the glucose these charges. And so here's a sheet of paper, and paper being made of basically glucose, comes from the starch of plants, have all of these charges kind of spread out on the fibers of the paper. Right, so here's my sheet of paper, and on the surface of the paper I've got all of these charges. Now, I'm going to dip the paper into the water. And what happens is, I dip the paper into the water, that the negative of one water is going to be attracted to the positive on this sheet of paper. And likewise, the negative of the paper will attract the positive of a water molecule. So the water molecules begin to be attracted, and they start to climb up and attach themselves with these dipole interactions to the sheet of paper. So this guy's going to come over here, and we're going to come over here, and so now we have a layer of water that has risen up. Here's the bottom of the paper, but notice that the water is starting to pull itself up the paper. And in fact, these molecules here will jump further up the paper. Oops, going up there. and they will continue to climb up the paper, hopping from one charge to another. Now, the nice thing is that these water molecules have two sides. So they have a positive side and a negative side. So they can be attracted to either the positive or the negative. And a lot of times what they do, because they're constantly wiggling and dancing due to what we call Brownian motion, that this water molecule can swing around and be attracted over here and then swing up there and be attracted up there, kind of like a monkey in a tree. So these water molecules are slowly climbing up the paper due to these electrostatic forces. Now, that's all in good. It makes what we call a microcurrent. The microcurrent of the water is to flow up the paper. Now, as the water flows up the paper, the water is also going to interact with our dye molecules. Now, let's take a look at, here's an average molecule of food coloring or any kind of dye. It's going to have on it, it's going to have positive charges and negative charges due to polar bonds within that dye. Now, here's the little dye molecule floating around it's stuck on the paper. So this water molecules are going to come by, and as the water molecules come by, the water molecules are going to attract. The positive side of the water molecule is going to attract the negative side of that dye. And as this water molecule rides up, it's going to pull that dye with it. And then over here, what can happen is the dye can swing around and grab this water, and then as this water is attracted further up the paper, that dye is going to ride with it. So the water not only climbs up the paper, okay, but it also pulls the dye with it because of these charges. Now, the microcurrent is flowing up the paper, and the dye is flowing up the paper also with the water because of the polar bonds on the dye molecule. Okay, so let's talk just a little bit more about the different dye molecules. So here I have a small dye molecule, a big dye molecule, and another big dye molecule that has like extra charges all around it. So the difference between these two, this guy is really, really big and this guy is really small. They have the same kinds of charges, basically, the same number of charges, but it's just a difference of size. And here we have a dye molecule that's roughly the same size, but this one has a lot more charge on it than this one does. Okay, so if we have a race, and it's these two dye molecules, and as the water is climbing up the paper, the water molecules are climbing up the paper, and they are pulling the dye molecules with them. They have equal attraction. Both of these dye molecules have an equal attraction for the water as the water is pulling them up the paper. But this one's lighter and this one's heavier. So which do you think is going to win the race? Well, I hope you said the lighter one, because that's true. The lighter one's going to have less inertia, and it's going to be able to, it's like a shopping cart. You know, when your shopping cart's empty, you can move it around really easily, and when your shopping cart is full, it's really hard to move around. So because this guy is really light, he's going to move up quickly, much more quickly than this guy is. So this dye is going to present itself higher on the paper than this dye will. Now, what about these two guys? Okay, let's ignore this for a second. Here we have dye molecules that are roughly the same size. As the water molecules move up the paper, what's going to happen with these guys? Well, they're roughly the same size. So size isn't going to matter much to us. What's going to matter here is the charge. And remember that water molecules have charges associated, very strong charges. They're very polar bonds. So as these two water molecules ride up and pull, this one is going to have a much stronger attraction for the dye molecule than this one is. So this one, as it rides up, it's going to break this connection, and then another one's going to have to pick it up and pull on it, and then that connection breaks, and then another one picks it up and pulls on it. Whereas this connection breaks much less often. So this guy is going to be able to ride up the wave of paper, the microcurrent, much more efficiently than this one is. So let's recap. Water molecule. Water molecule is polar because of the oxygen-hydrogen bond. Okay, very polar. It makes almost like a little triangle with a positive side on the base and a negative tip. Now, the reason why the water climbs up the paper is because the paper is made of glucose, and glucose has charges on it, and so the water molecules are attracted to those charges, and they climb up the paper due to dipole-dipole interactions. The dimolecules come in different sizes and different amounts of charge, and so the lighter ones are going to generally tend to climb up faster. Also, the ones with more charge are going to tend to climb up faster, and the heavier ones with less charge are not going to climb up as fast. Right. Well, there's a quick summary of paper chromatography. I hope that helps.